Welcome to Programming in Modern C++. We are in week 8 and in the last module of week 8, module 40. In the last two modules, we have discussed about templates as a generic solution for data structure reuse and looked at various algorithms for template instantiation and template parameters and how to use class template in inheritance hierarchy, had examples. In the present module, we are going to look at something new for your thoughts, that is called function objects or functors, and what is their utility in the standard template library. This will be the outline which will be available. Now, first as we mentioned about function, we will use a little bit of a generic term, say callable entities, something that can be called. So, I say a callable entity is an object that can be used in the same syntax as a function call and it will support in a way the function call operator simple parenthesis. That is how we get to know that something is a function, right. We say int add int, right. This is the signature, and then we say add 5,3. So, what tells me that add is a callable entity, this pair of parentheses, right. So, that is called the function call operator. These are typically known as function objects or functors also. Some authors distinguish between them with subtle differences in meaning. We will use them interchangeably depending on the context. Now, there are several callable entities in C++ which look like a function and calls something and does similar stuff. Naturally, you have seen function like macros. There are C functions, global or in the namespace. You have member functions, you have static, non-static, pointed to function, member functions which are static, non-static, and so on and so forth. Pointers to member functions that are static, non-static. You can have references. And you have functors, which are objects that define a function call operator. So, first let us look at function pointers, which have a very similar behavior. So, what is a function pointer? We have already studied. It is a address of a function. It could be address of an ordinary function, that is a C global function. It could be static C++ member function, it could be non-static C++ member functions, right. So, these are the three categories that we have seen, leaving aside macros which are more syntactically like a function, but it is not exactly a function because it does not go to the stack frame and all those protocols. So, a function pointer points to a function with specific signature. It needs to know what is the signature, that is list of calling parameter types, the return type, the calling convention, whether it is a C convention or a C++ convention or some other specific convention which is defined by the vendor, and so on and so forth. So, these are typical function pointers in C. You can define a function pointer and use that. You can use different calling conventions. Here there will be C calling convention, which is C declaration. Microsoft Visual C++ use some additional calling conventions for the Windows API particularly. You can assign address to a function pointer, right. You have a function pointer here, you have a function, you can assign that address by doing ampersand, and I had mentioned earlier as a shortcut, since you can only take the address of a function, nothing else. If you just write the name of the function also, it is taken to be the address of the function. Then you can compare two function pointers and get true or false, and call a function invoke a function pointed to by a function pointer. So, these are the things that a function pointer typically will allow you to do, right. So, function pointers in C you will do it in two ways possibly. One is directly, you have defined a function pointer, you have a function, you assign it to the function pointer that you have defined here, and then use that function pointer to dereference and invoke the function. Or you can type def it by this function pointer name. So, you are aliasing with the type, then define a function pointer f of that type, set a function pointer to that, set a function to that, and invoke f. So, these are the two typical ways that you will be using it in C. How about in C++? In C++, you can have function pointers as well as you can have function references. So, you can have function pointers like you had in C, but you can also have function pointers which are of a certain specific class, a class member. So, you are saying that this is a function pointer a colon colon star PT2 member, says that PT2 member is a function pointer to a member function of class A, because a member function of class A only can be referred to as a colon colon, where A is some class. So, in that if I define a class A and have a member function there, I will have a calling convention of C++ in this case, then I can assign the actual do it function to the function pointer by taking its address. The name of the function is a colon colon do it, I do ampersand to get the address and put it to the function pointer. Mind you, this function pointer is defined for a member function of A. So, I cannot take a member function of another class B and assign it here, that will be a type error. Right. I can compare two function pointers provided they match in their type. I can dereference the function pointer and I can actually use it for invocation. Right. So, what I am doing is I am dereferencing this to get the function, I am dereferencing this pointer to get the object, then the object dot member function is the invocation. Right. That is a simple way of doing this, just parsing back into the basic syntax. So, if we now summarize that what are the things that the function pointer can do, the operations, we see that we can assign, we can compare two function pointers, we can call a function, we can pass a function pointer as a parameter, we can return a function pointer from a function, we can have an array of function pointers, and these are involved in a variety of programming techniques that you can replace in switch if statement, if this type, if this type, if this type, this kind of things can be replaced by function pointers. It can be used for lead binding or it can be used in the case of callbacks. Right. So, these are all very similar mechanisms, but all of them use function pointer and used in different programming context. So, these examples we have seen before, but I am just bringing them in the context of the function pointer. So, here I am trying to evaluate an expression involving the different numbers and operators, and I have 4 different functions for doing that, and I have a opcode which says which operator is this. Depending on the operator, I call one of these functions. Okay. In the other case again, we have all these functions, but what we do is we define a function pointer generically which takes 2 floats and returns a float, which is the common type signature of all these 4 different operation functions. And then what I do is, instead of doing a switch on just the type, we say that we will do a switch on this function ampersand plus. So, instead of writing it through the code within quotes plus, I write it as a function pointer plus. So, I am saying that take a b and do a plus, take a b, do a minus, write that, right. So, this kind of switch, which is a nesting of if else statement, is replaced here, because here you see there is actually no switch remaining. All that is remaining is you just call this function pointer, because in that function pointer you have already specified the actual function. So, here what you need as a 2 level, first specifying the code and then doing an if else, can be simplified and made more semantically meaningful. So, this is the first context in which function pointers can be used. The other is what is known as late binding. Late binding is, I talked about this on some other context as well, and we have a separate tutorial on this as well. So, all that we are saying is, if I am trying to do a dynamic binding of my function, dynamic linking of my function, what does that mean? That I do not want to put the function as a part of my executable code. I just want to know that this is my signature, and at the runtime I will go to the system and find out what is the available implementation of that function and call that. So, the normal function binding is static, it is early, because as soon as I see the function, I need to know what is the function body. Here I am saying no, all that I need to know is just like the compile time, I just need to know what is the signature, but the function body can be supplied later on, which means it can be replaced even after I have written the code. Right? So, for that the mechanism is to use a specific header. Dynamic linking function is a name of the header, dlfcn.h, and with that you open your library and define a function pointer which takes a void, gives me a void, because you do not know in general what the function can be. So, you assume that it only can be void. And then what you do, you provide the name of the function that you want, so that it can go to the library and find out a function by that name and give you that pointer, and then you call that function. So, this function which you find in the library may have been generated after you have written the code for calling it, which is not the case with the early binding. Right? So, when you do that, you have got it finds and returns you a void star pointer, which you cast to your function pointer type, and then you call that particular based on that particular function pointer, which will actually call the hello function that you have provided at a later stage. Right? So, this late binding is required to provide any user defined linkages to any user defined code at a later stage. You have also seen late binding in terms of virtual functions, because you have seen that if you have a virtual function, then you do not actually know, the compiler actually does not know which function it is going to invoke, whether it is a base class function or the derived class function. It depends on the type of object that it is actually pointing to. So, both of these situations are in two different contexts, but both of them actually give you the same, need the same functionality of late binding, which means that the function to be called is not decided at the compile time, but it is decided at the runtime, given what particular function body is available. In the first case, you find out by searching the library explicitly. In the second case, this happens to the virtual function table and the runtime type of an object, but they are the same thing. So, this is the other context where function pointers are used. So, combining this, you can also have callbacks in the applications using function pointers. So, what do I have? I have a main, I have a function f which actually does nothing. I take that, I have a function pointer and I call the function g. Right? Now, this is my this is my main. So, that is this is my application code. In the library, what do I have? I have the same function pointer, and the signature is very simple: take a void, return a void, right. This is all that it has. And I say that the library has provided me a function g. Now, this function g needs to know the function func, which is only the user knows. So, until the user has provided that, the library cannot actually do anything. Now, naturally, you cannot make it a function directly, because then to build the library you will require the body of that function, which does not exist, right. So, you are making use of this function pointer here. Right. Now, what happens is if so main knows that the library will need to know a function pointer which is known as func. Right. So, the user application programmer will need to set that func to the function which it wants get called from the library. So, the way it happens is here from main you call g, and g calls this function back, it goes back and then it comes out. So, the library is achieving its objectives by using a function which you provide to it at a later point of time, and in every invocation you can have a different such function. So, this is exactly what we saw in terms of things like quicksort that is provided by the C standard library. So, this is how it goes. You start doing main calls g, control goes into the library, then it comes, it does something, comes to the function pointer. So, it tries to invoke the function which you have set to f here, which you have set to f here. So, it actually calls f, and as you do that, then your as you do that, your function f is executing. As f executes, it comes to an end, the control returns back to the library. So, this is the callback happening. So, what has happened is the library has called back into the application code and has got a functionality done embedded in it, and once this is done, then g comes back to main and the task has been completed. So, again using the function pointer you can have this kind of callback mechanisms. So, you can replace the if switch, you can do let binding, you can do callbacks, all of these you can do with function pointers, which is the most which gives you a lot of flexibility in terms of the way you do the entire thing. So, C uses this for actually giving you a generic sort function which is qsort, which is available in the standard library of C, where you give a pointer to base, which is an array containing a set of elements. You do not know, at the time of writing quicksort, you do not know whether you would want to sort an array of integer or of double or of a student or what. So, what you specify is you specify how many elements are there, which you need to know. You specify the size of every element. Look at, you are referring to it as void star. So, what you can get is only, you have a pointer to something you do not know, and then you are saying this is the size. So, you can take the size one after the other. So many bytes together forms one element. Right? But to be able to do quicksort, you need to be able to compare two elements, right, of the type you have given. So, you need to provide a compare function, and you provide that as a function pointer, because the library at the time of writing qsort does not know the type that you will compare. So, the library cannot write that, but all that it can say that it takes two pointers to two elements, does not know its type. So, the only way it can refer to it is their constant void star, that is, they are pointed to constant objects of no known type, and the result should be an int which gives you whether it is less or it is more or it is equal. Right? Now, when the application programmer actually wants to use it, the application programmer has to provide that function. It has to say that this is my function, and the application programmer knows the type of elements it has to compare. So, it casts into those types from void star, does the comparison. Here it is cast to int. So, int comparison will happen. If it is greater, it sets 1 as a return value, otherwise if it is equal 0, if it is less -1. So, this function now becomes eligible to work as a compare function pointer, right. So, this is something that the user is providing. So, you are going to use this as a QSort is going to use this as a callback to ask the user, okay, you have given me elements, but how to compare them. So, that is precisely what the QSort does. It takes your array as void star to match this, takes the number of elements, take the size of every element, which you have taken size of field 0, you could have done it size of int also, and then it takes this function pointer which it calls back to, right. So, this is the basic mechanism by which you can have user provided functionality to the library, right. This is what C has done always. Right. Now, there are a lot of issues with that, because there is no value semantics, there is no proper way to compare. All functions which take a void and returns a void are considered to be of the same type, which may not be what you want, and the type checking is almost not there. This is the point I mentioned, two function pointers having identical signature is necessarily indistinguishable, and you cannot capture the parameters. Right. Now, these are the issues that functors solve. So, what is a functor? It is a smart function. It is an object which may or may not have states, and it encapsulates a C or C++ function pointer. It uses template, it can engage in polymorphism, it has its own type, and the most important, it overloads the function invocation operator. Typically, functors are faster than ordinary functions. They can be used to implement callbacks, and we will see later on that they are part of a design pattern called command design pattern. So, these are some of the basic functors, right. For example, here just note the notation. This is the name of the operator and this is the function parameters. So, the operator is operator function call, it takes nothing, gives you nothing, whereas here the operator is operator function call, takes two integers, gives you an integer. So, like the way double does, right. So, these are the basic functors that you have, but we will be interested in something which is more interesting. So, this is the one slide memory that you should keep in mind. So, there is the adder function which is written in the classical way, a global function. This is an adder functor where what I have done is I have overloaded the function call operator to do this addition operator. Now, let us see what happens. We have x, y, we call the adder function, this will call this function, add the two numbers, give me the result. We all know that. I have a class adder functor. So, I have instantiated that as a adder functor object AF, and then I call AF xy, which is a notation which will shock you, because AF is an object, but I am using function call syntax with that. What does that mean? That means simply that AF being an object will take its operators as a shortcut of the detailed notation. So, AF, this operator means that AF dot operator function call. So, which means basically this function, and the function will get invoked. The advantage now is that you can actually overload this operator for different types. You can overload this operator for different number of parameters. And added to that, since this AF is an object, you can actually have a state of that. You can remember what that function was doing earlier and what it is going to do next, right. So, this is a big advantage. So, let me show you some examples from STL. STL has what is known as a, so this is the task. I want to fill up a vector with random numbers, right. I am using an STL component known as an algorithm, which gives me different algorithms. This algorithm is a generate algorithm. What does it take? Templatize takes a forward iterator that it will start from the left, go to the other end, and it takes a class generator. Now, generate takes the operators beginning and end, and this generator, which actually is a functor, which will do an operation, it will do a callback. And then what it does is it goes from first to last every time it is actually incrementing it, it is an iterator. So, it is going after the one after the other, and at every point it invokes this function pointer functor actually to generate a number and gets that. So, using this and say using a very simple generator like the rand function in the library, you can write for a vector v, this is your iterator begin, this is your iterator end, call rand as your functor, which will be called every time you go over this generation and do generate. So, what it will do? It will start from the beginning of the vector, keep on calling rand at every element and putting that value. The vector will get filled with the random values. So, that is how a functor can be used to write very simple and intuitive and compact code for us. Let us look at the sort. Suppose I want to sort a vector of double by magnitude, right. I again include algorithm which has a template algorithm for sort. What does it need to know? It needs to know the beginning and end of the iterator. I am using random iterators here, right, because it need to know what part, there has to be some sequence. It could be an array, it could be a list, whatever, I do not care, but I will iterate and go from here to here and to be able to sort that. And I need to know a comparison functor like we needed in qsort to be given in a complicated manner. So, what it will do with this first and last specified, it will go over this entire collection and actually use the comp functor to do the comparison and do the sorting. So, that is a nice beautiful solution, and we can compare it with the quicksort solution to see what we get. This is left side is the solution in C and C library using the quicksort example. This is your quicksort signature, quite complicated, you just do not know what it means. This is your sort signature, which is very simple and straightforward. You tell the range and the compare functor. That is all you need to know to compare, to sort a range of elements. This is your comparison functor, less magnitude. This is how you have to write it in C, take it in void star, cast it to double star, then dereference a double star, and all complicated. Here you write it very simply as a Boolean operator, because it has to, it is a functor. So, what it will do? It will do a function invocation taking two double and returning a bool, and all that you need to do is to actually just do the comparison of the double. Now, the question is, how will sort know that this kind of a function, this kind of an interface exists? That is why you provide the library provides a template binary function which has three parameters, three type parameters, binary function. So, it will take two parameters for that function. So, the types of those, and this is a return type. Right. So, it becomes very easy for the sort to know that you are providing what kind of a binary function for doing the comparison. Okay. So, actual code, you just look at the call here, quick sort, this we have already seen, and here it actually says what it does. Start at the beginning, go up to the end, use less mag. I have just used struct here for place of class, because I need this to be public. So, having written struct, I may not actually write this as this is different. This is for the inheritance actually. So, it publicly inherits, this less mag inherits from the binary function template, which says that it is a binary function taking 2 double and a bool and implements it. And the interface that you actually have to call it is so simple. Right? So, this is a very powerful use of functors in the context of the library. Know that this does not have a state, because the functor did not need to use any data member. We can also have states in this. So, for example, I want to compute the sum of n elements in a vector. Vector has n elements, I want to compare that. So, what I do use here is an algorithm called for each, that is, do for every element as you go in the iteration from first to last, right, and apply this functor f n. Right. It can be used for any purpose. Right. So, it goes from first to last, just applies this f n on the current element, goes to the next element. Right. I am going to use this for each to add the elements of a vector. So, I am defining a functor adder deriving from the template of unary function. That is, I just need one parameter and it will return a void, that it will not return anything. Right? So, what does that do? That simply constructs an adder. Right? And what does the adder have? The adder has a local state, a data member sum. That is, it will have two things. One is, it has the function call operator to make a call every time, and it has a local state sum where it can keep the sum. Right? And I encapsulate both of them in terms of this adder functor, adder of class. So, I define a vector, I do for each on this part is routine, go from here to here, and as functor I pass adder. So, what will happen? The first, when this is called at the beginning, adder is got constructed, I have given it here. So, sum is initialized to 0, this is initialized to 0, and then it will call it is calling this f n, which is this function, which is adder, the object function, which is the function call operator here. So, it calls that. So, whatever is the sum, x gets added to it. What is x? What has been passed, the current value. That is added to it, stays as a part of the functor. I do not need to have a separate sum variable. I again go to the next in the iteration. Again this gets invoked. So, the sum which had the first element now, to that the second element gets added. It goes on in this way, and all elements get added over this time. So, this is a very beautiful way to see how functors can be used with state. We will have a separate tutorial on this as well, because this is a little bit involved, and we will have lot of illustrations of this when we go to the modern C++ part. But I just wanted to introduce this basic concept of function objects, where objects can have function call operator and can be used for invoking functions with or without state. Thank you very much for your attention. We will meet in the next module next week.